All right, so next we're moving on to trigonometry. Now, when it comes to trig, I know that for most people, it is their most feared and hated part of maths. I remember a lot of people used to struggle with this at school, and even though I loved doing this, I still used to think to myself, when am I ever going to use this? Basic maths like addition, subtraction, you think, okay, cool, that's fine. I need to count my, like do a budget or something. But trig just seemed so far from being practical at all. And so ironic that it literally is used on a daily basis in 3D, right? It's actually one of the most practical maths. It's used a lot in construction and architecture. It's just really, really fascinating and powerful mathematics. But again, there's a stigma to it, and so let's try and dissolve that and examine it kind of in a more practical and visual way, and hopefully that will then make sense and kind of take away that sting of having to learn trig again. So we're going to examine the three main functions that we use here, but I'm going to just, so you can see them kind of here on this graph, but I'm going to switch them off and we're going to look at them one at a time, and then we'll sort of we'll discuss how they interact. So I have a graph here. I've got x and y, right? My y goes into the negative just because obviously we really need to see that. My x just goes along positive here, okay? And what we have is a sine function, okay? So with sine, what you're essentially doing is you just feed it a number, okay? So sine of a particular number returns a certain result. But what we feed in here for this theta, right? If you ever hear them refer to it as theta, that's this symbol, right? So it's just literally a variable saying, okay, whatever angle we feed into this sine function will then be called theta, and that just returns a value, okay? Now, how we get it to form a graph like this is because what we're doing is we're feeding it multiple x values. See, we've got points all along this curve, and so the points have different x values. And so if we use x as part of theta, right? So if we just said sine of x, then we would get a sort of a wave forming along this line, because as the x value increases, it moves through the sine wave, okay? And so what we're doing is we're setting the y value of our points based on the sine of x, okay? But there's a few extra steps that we're doing here in order to get this, to be able to manipulate this wave, because if we just fed it a normal, just by default, then we actually end up with something that looks like this, okay? Which, yes, is actually still doing the wave, but it's so large we would have to zoom way out to see this eventually form the same kind of wave. So we want to be able to alter the frequency of this wave. We also want to be able to offset it, because maybe we don't want to start at 0, but we want to sort of start it a little bit back, right? And we want to be able to manipulate the overall amplitude of the sine wave, because -1 to 1 is great, but what if I want more out of it? What if I want to then apply that to something like maybe, huge waves in an ocean or something? So we can then have an amplitude as well. Now, this sort of methodology here of how to apply frequency, offset, and amplitude is something very important to learn, okay? So let's have a look at this. We'll talk about the radians just now, but let's just have a look at, first of all, frequency and offset. So we said we were going to have sine x, which is actually what we're looking at here, is sine x. But this x value, right? See here, as the x value gets higher, we're essentially sampling from further along the sine wave. So if we multiply our x value, then what we're doing is essentially just sort of reaching further along the sine wave for every value we have in x. And so we're going to scale down the wave along x. Okay, so we multiply by our frequency, and then we can add an additional random number. Like this number could be anything we want it to be, and all it's doing is saying, okay, well, if you're at the 0 point, then you want to sample at the point of this 0 in the sine wave, but you go, oh no, but actually I want you at the value at 0, I want you to actually sample at 5. Okay. And so you can literally just add an offset where it will then go and sample that different value, right? And the result is that it moves our wave left and right. So let's see what happens here is as I increase frequency, like I said, the x value is searching further along the wave and therefore making the wave appear as though it is shorter, okay? So the actual wavelength is shortening, right? So I'm going to take this back to 90 where I had it before. So this lets us just, we can scale it up or down, and this is our frequency. And then our offset, like I said, is just a number that is going to essentially move the wave left or right because it's just changing per point where we're sampling this wave. Okay, and so I can move it left or right. Now, it's very important whenever you do this that offset is added after frequency is multiplied. Okay, if you think about it logically, you'll understand why. We have our x value, right, and we're multiplying by 90. And then let's say our offset is 5. Well, in this case, it's saying x times 90. So let's say x was 1, then we'll have 90, and then plus 5. So we're just sampling at 95. But if we had our frequency after our offset, what that would do is mean that frequency would be multiplying not only x, but also it would be multiplying our offset. So it would be 90 times 5 would be what we're adding to the whole thing, because we go x plus 5. So let's say x is 1. So it will be x plus 5 is 6. And then it will be 6 times 90. So our offset being included in that value means that the offset is being multiplied, which means that the higher our frequency goes, our offset changes as well. You will still be able to, if you did it that way, you could manipulate the numbers and eventually get to the exact same graph, which is fine. But then when you want to just go and move the offset and move it backwards and forwards, depending on how high your frequency is, your offset will move like maybe incredibly fast or dismally like slow, so that it, because depending on whether we're multiplying really, really high frequency or really low frequency will then determine how strong the offset is, and that's not what we want. So if you add offset after frequency, then offset is kind of isolated and it does only what it does. So it doesn't matter if our frequency is really, really high, it's still, our offset moves the points at the same speed essentially. Okay, so very important that to understand. And then you see that amplitude is a multiplier after the whole sine function. That's because what we're wanting to do is the amplitude shouldn't alter the angle of the sine function at all. It should just take the ultimate result of this, which goes from -1 to 1, and says, let's just change those numbers to be -2 to 2. Okay, so if we take the amplitude to 2, all it's doing is just multiplying the result. And that's where amplitude belongs, is after the entire function has been run. Do not put your amplitude inside of this function, or your amplitude will be acting essentially like a frequency, multiplying the angle, not multiplying the actual result of the sine wave. Okay, so this is just a really important function to remember. And an important part of this is to know that sine function, all the trig functions, expect degrees in radians. So radian is literally just 57.3, well, in fact, it even has other point something degrees. Okay, it's just a straight conversion, right? There is no, it's not a complex function or whatever. It is an actual, just a multiplier. So you could not run the radians function. You could drop this from it, but then if you set your frequency to 90, it will not match mine over here, which is set to 90. Instead, it will just be, a lot sort of smaller, right? So you can not use the radians, but then it becomes harder to work because you want to feed it degrees. You want to, for example, let's say you want something at sine 90, but you want 90 degrees, but the sine function expects radians. So if you just use this radians function, and you'll find that function exists in Vex, as the function is literally called radians, and there's another function called degrees, so you can convert backwards and forwards between radians and degrees. And then in VOPS, you'll find there are two nodes, one called degrees to radians, and the other one radians to degrees, and they convert the same way. Or you could literally just multiply by this amount if you really wanted to, but it's why would you want to do that? So this is how we essentially apply a trig function, okay? And this is the result that we get. So let's have a look now at cos, okay? So you'll see our cos value. I mean, our expression is the exact same here, except we're running cos. Now, cos is cosine, okay? So it's just sort of the converse value of sine. And what that means is basically it's just a sine wave, but that is offset by a full kind of like a quarter, right? So if we had to change the offset of our cos wave, you'll find that you can eventually have them reach and overlap exactly, okay? Or we could go the other way as well. So you could offset it this way and eventually have them overlap exactly. And it's basically at 90 degrees, right? So they are 90 degrees off from one another, okay? So where sine of 90 degrees, well then you'd have to have cos of 0 degrees, and that's when they would be exactly the same, okay? So this can be very, very useful for us, and you'll see why. I'm going to show you just now an example of how we're going to use the sine and cos waves, but it's just good to know that they are just literally an offset of one another by sort of a quarter of a cycle. Because you'll see here the waves go, so our cos starts at 1, our sine starts at 0. So with sine, it goes 0, 1, 0, -1. And then that cycle repeats. So it goes 0, 1, 0, -1. And it just keeps repeating, okay? And if it's got the same frequency, our cos wave will be just offset from that. So it'll start on 1 and then go 0, -1, 0, 1. It's following the same loop, but it's just offset. So it starts from 1 instead of starting from 0. Of course, if we have different frequencies, then there is going to be no correlation between these two. But it's if they share the same frequency, then the offset will essentially align them. Okay, and of course you can also have them follow a different amplitude if you absolutely wanted to. Okay, also if you wanted them to be, let's say, almost like a DNA strand, like just aligned in exactly halfway, then you'd have to go positive 90, so you go the other way, and you'll see here that whenever they both start at 0, but when this gets to 1, then this gets to -1. So it's essentially a negated sine wave would be then a cos wave with offsets to, so cos of 180 is the negated version of sine of 90 degrees. Okay. Now, I'll show you, as I said, how this helps us practically. But it's just fun and interesting to kind of see how they relate to one another. And then when you are using them, then it kind of makes a little bit more sense and you understand what they're doing. Okay. Now, so the tangent graph, this is quite a bizarre function. It does have some practical uses, but mostly in just sort of much more complicated mathematical functions. If you're ever following maybe some kind of scientific paper to get like, maybe tangent drag or something weird, and you can see on a paper there's a mathematical function, then they may be using a tan function, and so now you know that it exists and you can use it the same way. But really, it tends to be not that practical beyond those, because it does very strange things. It goes basically from infinitely small, so like as close to zero as it can get without really touching zero, and then sort of eases into zero. Not zero. As far it's like in infinity, like negative infinity, that's what I'm trying to say. It goes from negative infinity, it eases into zero, and then it ramps out, so it eases out into infinity, okay? And then it suddenly, when it crosses a certain threshold, then jumps right back down. So that you don't see, it doesn't actually ease back down. It literally just, once it almost basically reaches a certain kind of threshold at the top, it then jumps to the bottom and enters again. It's very, very strange. So I don't know if you'll find many practical uses for this function. You might at some points, if you want something to maybe enter the screen, so like screen left, and kind of ease into the center of the frame and kind of go slower, and then move out of the frame again to the right, and then re-enter on the left. Then you could kind of put your maybe your x position value through a tan function, and so it would kind of ease into the center, then go out, and then loop back around. You might end up with weird velocities happening when it does the jump from here to here, though, so you might end up with streaks if you have motion blur on, so be very careful of that type of thing. But you might find some outlying sort of cases for the use of tan, but I have honestly never used it kind of in all of my time of doing 3D. Okay, it's nice to know that it's there, and if you're following a mathematical sort of paper, maybe they'll use it in a complex function, but certainly not just practically going, I'm just going to put a tan function in a parameter. But you will do that with sine and cos, because they can be very useful. You can have something kind of ease in, ease out, like just loop backwards and forwards, maybe the release of particles, or sort of the direction that the particle's moving. So they move along positive, then negative, positive, and negative, and so you can have things kind of rise and fall. Okay, so all right, so let's move on to then actually, I just want to show you here. So if we look at a single value of x along these, okay, because I know we're looking at a wave, okay, and we often think of trigonometry functions as waves, and that's because we're feeding it a variety of x values. So essentially an array of x values, a line with different values along. But we can also, if we sample at a single point, you'll see what happens to the values. So here is my y result. So my result of sine, cos, and tan, if my x is this. Okay, so with an x value of 1, then my sine is 1, my cos is 0, and then you'll see the tan is like just crazy negative number. Okay, so it's way down at the bottom. Okay, and then as we increase this, you'll see what happens. So the sine and cos functions then do their normal kind of pivoting from -1 to 1, backwards and forwards. They just sort of modulate right between those two. But then tan does this wild, jumps up and jumps down. Okay, so that's just so you can kind of see what happens when we sample it at a particular point. So if you fed, let's say, sine, but not with a variety of values, like x is a variable, but literally you said sine of 90 degrees. So you'd go radians 90. Sine radians 90 will just return so 90 would be 1 times 90, right? So if we're sampling at 1, this is what it would be. So sine radians 90 is going to give you a value of 1. Sine of 0 is going to give you a value of 0, but cos of 0 radians is going to give you 1. Okay. So now let's move on to something practical. Let's actually see how this works for us and how we can use this in 3D, because it's all fine and well to understand how the maths of it works, but you know, if it's not practical, then really what's the point? So here I've got a circle, and it's important to note that, you know, when we're talking about trig functions, circles are going to come up quite often, because although it doesn't look like it, these curves, and in particularly the change in angle, the exact way that it eases in and out, is highly important. Okay, this is not just a normal ease in and out. This is ease in and out sort of with a ratio that relates to pi. And we all know whenever you talk about pi, really you're referring to a circle in some way. Okay, so the exact way that it eases in and out is the same way that a sort of the angle changes on a circle, right? So we're going to examine that, because we can use trig functions to do some really cool things to curves and circles. Okay. So we've got a circle here, and it's moving. I've got a point moving along this circle, okay, on my timeline. So when I click play, it literally is just looping around. Okay. Now, what I want to show you is how that relates if we just isolate one of these two axes. Okay. So if I switch on my green point first, what this is doing is following just the y value of this. So you can see at every single frame, the green and the white have the same y value. Okay, they're not doing anything different. The only thing is that the x value, so left and right, is stripped out of the green. Okay, so it's not moving left and right at all, but it is following the up and down of it exactly the same. Right? And if I create my blue point over here, you'll see that it's doing the exact same thing, but just the left and right and not the up and down. Okay. Now watch what happens. These two do kind of strange things. Look at when the green point touches the bottom and top, and at which point the blue point is when it does. Okay. Let's kind of do this. If we start at 1, you'll see here that our green point is in the center and blue is on the edge. Then as it rises up, you'll see that first of all, let's note the fact that the green slows down a little as it reaches the top. So it's not just linear, it's not just ping-ponging backwards and forwards, but it's actually easing at the top and bottom. Okay, so it's at its fastest when it's in the center, and then toward the end it slows down, and you'll see that before it starts moving again, this blue point is in the center. So this is in the center when this is at the top. And then this is at its center when this is on the far left. And so whenever one is on the extreme, the other is on the center. Okay. So now that we've noted that, let's take a look at this. If I had to take this curve, so this green point, and let's say we had to sort of trail it out along x. So if it was emitting particles along x at a constant velocity, and we sort of connected all of those particles into a curve, this is what it would look like. Okay, so we're releasing these particles but just joining them in a line, and look at what's actually happening with the sort of the peaks and troughs. Right, so do you recognize this? That is exactly what is happening here in our sine wave. So a circle is following a sine wave on one of its axes. Okay, now let's switch on our blue and see what's happening. Now the same thing here. If we had to release particles up on a constant velocity and move left and right and join them, you'd see that this forms another wave, right? But we also know from what we noted just now that these are offset from one another. Okay, so if I blend here, what I'm going to show you, I'm going to overlay this blue one. I'm literally just rotating it around the center over here. So I'm just pivoting it. So if I put them on top of one another, Okay, so it's still being created. It's the exact same curve. I haven't changed it, but I've literally just rotated it 90 so that they are on top of one another. Now, look how familiar that looks to what we're looking at on the left here. Okay, that is exactly the same thing, right? So we have essentially a sine wave and a cos wave, or you could think of it as two sine waves, but one is offset by 90 degrees, or you could even say it's two cos waves with 90 degrees, because that is exactly what sine and cos are. It's just the same but offset. Okay, and so this is how we form a circle. If we had to move our point, let's look at our y point again and say, well, you move along y and slowly slow down. And so in this first quarter, y is increasing, but x, so the blue is decreasing. Then blue continues to decrease, but it decelerates. But at this crossover point, y, so the green, starts to move downwards and it accelerates. And then at this point, it's at its fastest, so green starts to decelerate, but blue actually slows down, stops, and then reverses its direction. And that's what's happening in each quarter of the circle. Is there's one thing is changing from accelerating to decelerating, and the other one is changing directions completely, and it's beginning to accelerate in the opposite direction. And that's how we form a circle. Okay, so now how do we take that information and the relationship between trig and circles and make it practical? Okay, so I have on the right here a line, okay, and I've polywired it just so that we can see it more clearly, so it's a bit thicker. Okay, so we've got just a straight line. Got a bunch of points along this, and they're going along y. So what I'm going to do is use y instead of over here where we're using x as the sort of the sample location, so the angle of our trig function. Saying where along the curve are we? Well, x determines where we are. In this case, because I want to just do this vertically, I'm using y, but it's exactly the same thing, okay? And I have a vex function in here. Now, I know that some people that are watching this course maybe don't know vex very well. Maybe you use VOPs, and that's fine. That's totally fine. What I'm going to do here in vex is very, very simple. So simple, it's basically what we've just done over here, is just writing this function out. So please note that you can do this in VOPs just as easily, okay? But I just wanted to show you here in the most simple form how we can literally just write out the function and turn this into a cool shape, okay? So what we're going to do is, so for those who don't know vex very well, don't really worry too much about the syntax. It's not really that important. What I'm wanting to show you is just how the function is applied. So what I'm doing is I'm setting my x value of the position on these, so the points on this curve, and I'm setting that value to be equal to a sine function, right? So I'm going to create a sine function, and inside of this sine function, I know that it wants radians, but I want to work in degrees. So I'm going to put a radians function, and so now everything I put inside of these brackets can be degrees, and then the function will convert it to radians for me and then feed it into the sine graph, okay, the sine function. And now what I want in here is exactly what we had over here, right? So we've done sine, radians, and now we're wanting to basically take our sample value, so our theta, but multiply that by a frequency, add an offset, and then multiply the whole thing by an amplitude. So that's what I'm going to do over here, right? So inside of here, I'm going to say v at p dot y. So I'm taking my y value, which is my theta, multiplied by, and I already have a function set up over here, a variable called freq, so freq for frequency, okay, which is grabbing my frequency from my parameters over here. And then I'm adding my offset, which is just a variable called off, right? So please note that I multiplied first, then added. Okay, so you see that this is being multiplied, then I'm adding my offset. Okay, and then I'm going to take outside of all of the brackets, so outside of the entire sine function, I'm going to multiply by amp. And again, amp is a variable that I've already set up to be a reference to this parameter. Okay, so now I can create a sine wave, but like in 3D, I can control the frequency, I can control the offset of this wave, and I can control the amplitude of it, right? So what I'm going to do here now is we're going to take the same function, because if we look at it in a three-dimensional sort of space here, we've got a flat wave, okay, which is fine, and this may be what we kind of want for certain scenarios. But I want to do something a little bit cool, and I want to relate to sort of what we learned here about circles and the sort of ratio between sine and cos and how these interact. Okay, so what I'm going to do is also offset my point's position, but I'm going to offset it on the z-axis over here. So backwards and forwards will be offset by a different function, not a sine function, but a cos instead. So we're going to say v at p dot z, and then I'm going to run a cos function, but with the exact same variables here. I'm still using my y as the sample. I'm still using my same frequency, so the frequencies will match, and I'm using the same offset and amplitude. Okay, and you'll see when I now click away, it runs that function, and from the front it looks exactly the same. But take a look at what we've formed in 3D, right? So because we're pivoting around the y, if we looked at it from the top, what it is doing is essentially the same things we were doing just now. It's forming a circle, because as that y increases, so it's essentially doing the sine and cos functions in sort of tangential axes. So x and z are having two different functions applied, and so it forms a circle, but along y it's linear, and so what it does is it forms a spiral. Okay, so this is really cool because we can use this for creating, you know, curls and braids, in like if you want to do hair. I've also very recently used this for doing like fireworks, or you know, you can have like maybe some magic, like a character releases a fireball. Well, what you could do is have a straight curve, but you could, just using sine and cos, could turn that curve into a spiral, and so that maybe that fireball that's thrown by the character would, like, you know, spiral around in you know, and you can change, you know, you can manipulate the frequency of this. So you could, I mean, you could create an actual spring, you know, like what looks like an actual spring. So you could use this for procedural modeling. You could take this much lower and kind of you know, alter this. You could maybe have like big spiraling vortex. Like you could use this for velocities. There's loads of things that you can do, right? And in fact, if our y is not offset, if we had to clamp our y down to 0, you know, v at p dot y equals 0, then we end up with a circle, you know. So like, and in fact, you can carve that circle based on our frequency. So you see here, I can form the circle and carve it back. So there's lots of really cool things we can do with this. And trig is so practical. That's what I was saying when we first started. It's one of those weird ones where everybody avoids it, everyone struggles with it until you've kind of eventually get it. And when you get it, it's so practical, because in 3D, the amount of times we use circles of some kind is really high. And trig and circles and pi are all kind of interrelated. Right. So I hope that you found this useful and practical, and that we've kind of hopefully broken the stigma of trig